Good afternoon, everybody. I'm Christophe Coreixas, and this afternoon I will talk about the collision models that are used generally for isothermal lattice Boltzmann methods. So let's start first with, let's say, the main ideas behind every type of collision model. So first of all, the BGK collision model. In fact, it's an approximation of Boltzmann collision model for which you assume that populations are close to the equilibrium. So in fact, it's a first order Taylor expansion of the collision model around the equilibrium. Most of the time, this equilibrium is defined as second order one, meaning that it's a sum of polynomial, Hermite polynomials up to the second order. Then there is a second type of collision model that is based on, let's say, multi-relaxation times. The main idea here is to relax every moment in a particular moment space so that you will be able to increase both at the same time the physics, because you will be able to control more moments, as well as the relaxation, which will eventually help you improving the stability. So generally, this moment space is defined in a reference frame at rest, which impacts directly at the numerics. And it is based also on the second order equilibrium, which impacts both the numerics and the physics. In fact, there are several types of MRT collision models, depending on the moment space that you are considering. The second type of MRT collision model is based on, let's say, central Hermite moment space, meaning that now the collision is applied in a moment space that is defined in a co-moving reference frame, and which is usually based also on an extended equilibrium state. And the last type of, let's say, moment space that you can encounter in the literature is the cumulant space, which with the cumulants being nonlinear combinations of central moment space. That's why, in fact, usually you are not able to write the collision models in terms of products of matrices, because it implies nonlinear transformations of moments. The third type of collision models is based on, let's say, a type of regularization step, which means that what we want to do here, it's in order to improve the stability, we want to filter out high order contributions of the populations directly. So what we do here is that we do a Chapman expansion of populations, and we only keep the first two terms, F0 and F1. F0 being the equilibrium and F1 being the first order non-equilibrium part at the Navier-Stokes level. So concretely, there are several ways to compute this non-equilibrium part. The first one is to project it on the Hermite polynomial basis. That's the projection-based regularization, PR, which is the standard regularization that was introduced by Jonas and Bastien Chopin. The second, this one, is based on a filtering mechanism that will improve the numerics by improving the stability. And it can be defined either based on a second order or on an extended equilibrium. The second type of regularization is called the Recursive-Regularization Step. So what we do here is that in addition to the projection of some let's say, Hermite coefficients, we compute the higher order one using a recursive formula that are directly derived from the Chapman-Xcock expansion, so that we will be able to better control the filtering out of higher order contributions. These are also based on the extended equilibrium. And last way of computing, let's say, this non-equilibrium part, it's through an hybrid formulation, because what we want to do here is to completely filter out high order contributions. But the fact is that for the second order coefficient, you have F minus F equilibrium that appears, in fact, in the definition, meaning that there are still high order contributions that are not completely filtered out. So the main idea here is to compute this term through an hybrid formulation that will be based on sigma times the finite difference approach plus 1 minus sigma the LB standard approach. The fourth kind of collision model is based on, let's say, a particular kind of entropic formulation, meaning that depending on an H functional, what we will want to do is to enforce a particular H theorem, which will eventually lead to a kinematic viscosity that will depend on both space and time. Usually, there is no analytical solution to this problem. So what people do is that they use root-fighting solvers. So root-fighting solvers, they have the advantage that they will allow you to find a numerical solution to the problem, but depending on the kind of solver that you will use, you may have like some discrepancies in terms of accuracy and or stability. In addition to that, the fact that you need to solve a minimize the H functional at each point of the grid and at each time step, this can be really time consuming. So that's why other people also propose, let's say, simplification of this problem through analytical formulation based on either entropic limiters or the new formulation, essentially entropic lattice Boltzmann method. Here, the entropic mechanism is what allows you to obtain stable simulations. And by playing with the equilibrium, you can recover more or less physics. Here, you can either encounter in the literature the entropic formulation based on second order equilibrium or extended equilibrium. Last of this formulation, which is not really, let's say, an entropic formulation because you are not really modifying anymore the viscosity here, is the KBC formulation that consists in a separation of contributions. So you will separate the kinetic, shear, and high order contributions in your population. And what you will do is that you will, in a dynamic way, more damp, depending a given formalism, the high order contribution, which corresponds in fact to a kind of dynamic MRT. Last but not least are the subgrid scale models that are usually used in the context of Navier-Stokes solvers. So the aim of subgrid scale models is to mimic properties of turbulence, especially in under-resolved configuration, where you know that you won't be able to solve all the turbulence scales down to the Kolmogorov. So what you do here is that in order to mimic the dissipative properties of vortices at the Kolmogorov scale, what you do here is that you modify locally the kinematic viscosity by taking into account a turbulent kinematic viscosity that will follow some, let's say, physical rules, such as the Smagorowski rule. That is, let's say, based on CS, which is the Smagorowski constant that is obtained experimentally, delta, which is the smallest cell size of your mesh, and the square root of the shear stress, in fact. Unfortunately, this formulation does not tend towards zero close to walls, while we know from both experiments and theoretical derivation that the turbulent viscosity should tend towards zero when we are close to the walls. That's why there are other formulations, such as the wall-adapting local eddy viscosity, the whale model, that impose the correct decrease of the eddy viscosity close to the walls. This can also be obtained with the Smagorowski approach by considering more, let's say, complex formulations, such as the Van Dries, dynamic or shear-improved Smagorowski models. The last one of this subgrid scale model is a bit different in the sense that here what you will do is that you will really work in the Fourier space, meaning that you will have a viscosity that will depend on the size of the local vortices, meaning that you will be to properly dissipate only the smallest vortices in your simulation domain through a space filtering. But one of the main, let's say, disadvantage of this approach is that it will increase the stencil, the communication, let's say, stencil communication of your lattice Boltzmann method, which will decrease the parallel efficiency of that code. So even though it's theoretically the best approach to account for subgrid phenomena, it is not that used, in fact. So if I sum up, there are let's say five families of collision models, which can be combined. In fact, you could, for example, think of an entropic formulation that is also based on moment spaces. There are many moment spaces, such as row moment space, Hermite moment space, central moment space, central Hermite moment space, and cumulant space. You could also choose to either work on an orthogonal or non-orthogonal moment space. For each of these moments, you have one relaxation time that needs to be tuned when it's not related to a physical parameter. So this increases the number of possibilities. Regarding the regularization procedure, you could also couple it with MRT or with entropic. And you have many ways of computing the non-equilibrium part, which further increases the number of possibilities. It's the same for the entropic formulation. You could choose different H functional or entropic formalism, depending on what you want to do. And it's the same for also the subscript scale model. So what I want further to add about the collision model is that there is a common misconception, let's say, regarding each of them. Meaning that sometimes in the literature, you might read that some collision models are more physical than other ones because, I don't know, they have like better Galilean invariance properties or so, that kind of thing. But in fact, if you look at the equation, here on top, you have the Navier-Stokes-Fourier equation, and on the bottom, you have, let's say, its counterpart in terms of moments of the equilibrium population. And what you can see here is that, in fact, the physics it's entirely controlled by the equilibrium population, meaning that if you take two collision models with the same equilibrium, in fact, they will have exactly the same physics. The only thing that will change is the numerics. So in fact, let's say that it's not that interesting from the academic point of view, but from the practical point of view, it's interesting because you can see that each collision model is just a button that you will push in order to have a stable simulation. So do you have any question regarding that part?
About the turbulence models. I mean, in many turbulence models, the turbulent viscosity is the only thing that changes.
Yes.
So, for example, in open form, you can just plug in pretty much any turbulence model and everything else stays the same. Is there something similar in Palabos?
In Palabos, I think that you have for sure the Smagorinsky models. I think that you have both the static and the dynamic version of the Smagorinsky model, but I might be wrong.
I'm not sure the dynamic version is fully tested, but there is a tentative for sure.
Okay, and what about space filtering?
I don't think it is in it, although I have it somewhere. And
yeah. that's what I thought, because I think I read a paper about it at some point.
There was an implementation, but it's not that efficient, so I decided not to include it in Palabos.
Exactly.
So is there any plans on including something like that? I mean, I don't understand the architecture of Palabos, but it kind of sounds obvious coming from open form background.
What do you mean to include what? You mean more turbulence models?
I mean, kind of like an architecture thing that you could just leave pretty much everything else as it is and just change the way the turbulent viscosity is calculated.
Oh, you mean being able to give your own turbulent viscosity, your own formula?
Yes, basically.
Yeah, so there is no general framework, but you can dig into these. So it's quite easy to do. So there is no config file where you can parse your own formula, but it's not very difficult to do in the code. If you're interested, maybe we can have a look on how to do that.
Yeah, I think it's not like super complicated. It will just depend on the formula, in fact. But I would say that most things that are required to the computation of the turbulent viscosity, you can easily compute it with Palabos.
Okay, thank you.
You're welcome. Other questions before moving to the next part? No. Okay, let's go. So now let's talk about the unified formalism that has just been introduced in Palabos in order to write all the collision models using the same type of formulas and the same type of code. So the starting point here is to look at the collision in the raw moment space. So here we move to a matrix formulation of post-collision population, which are noted here F star. This one is based on a polynomial basis that is composed simply of monomials of the discrete velocity Ci. Thanks to this polynomial basis, you are able to construct, in fact, a matrix that will allow you to move from the velocity space to the raw moment space. Once you have this matrix, if you compute its inverse, you will be able to come back to the velocity space starting from the raw moment space. And this is super important here, in fact, because we can simply rewrite these formulas such as this. Meaning that if you have M star, which are the post-collision raw moment, you will be able to, let's say, rewrite all the formulas in the velocity space, which is in fact the only one that you can use if you want to account at the same time, for example, for MRT models that are based on, let's say, linear transformation, and those that are not based on linear transformation, such as the cumulant collision model. So how does it work? So if you take, in fact, the first line of this matrix, it will give you the formulation of population at rest, with the first term being M00, with MPQ defined just above. And it's pretty simple, in fact, to compute all the population like this, just depending on the kind of velocity that you want. So here, plus a minus 1 along the x-axis, or along the y-axis, or in the diagonals. It's super simple. All the formulas are super simple. And the fact that you are using, in fact, the formulation in the velocity space, it prevents you from matrix products, meaning that we'll have formulation that will be much more efficient from the CPU time point of view. So this is the starting point, in fact, because what we can do, sorry, there is something before. So as I said before, the only thing that you need now in order to compute the post-collision population is to compute the post-collision moments. And by doing that, in fact, it's very simple to include either the multi-relaxation time formalism, the entropic one, which will only modify omega nu, that is related to the viscosity, or to add subgrid scale models, in fact. So now that we know how to, let's say, include all of this formalism in the raw moment space, how do we do if we want to, I don't know, compute, let's say, the collision step in the central Hermite moment space? In fact, it's also quite simple. We use exactly the same formulas. So we compute post-collision central Hermite moments. And then we just need to come back to the raw moments following very simple, let's say, conversion formulas that will allow us in the first time to go from central Hermite moments to Hermite moments. Once you have post-collision Hermite moments, you just need to come back to post-collision raw moments. And then you compute the post-collision population using post-collision raw moments. So just with this formula. So in fact, it's super simple. We can do it for any kind of moment space. So central Hermite moment space, Hermite moment space, cumulant, central moment. There is only maybe one little technicality when it comes to the regularization collision models. Is that here, in fact, I slightly rewrited the way we compute the post-collision Hermite moments, because regularization is based on Hermite moments, in fact. It's here that we need to recompute the non-equilibrium moment, in fact. And this can be done using the formula that you presented at the beginning of the presentation. And we are indeed able to recover both the standard regularization procedure where there is no recursive computation of high order moments. And you can even show, this is not shown here, that by imposing only one relaxation time, meaning that high order relaxation time, they are equal to tau, in fact, you are even able to show that the standard recursive regularization procedure is in fact a simple regularization in the central Hermite moment space, which is not the case anymore if you use an MRT formulation. Do you have any question regarding that part? No question at all? Maybe I would just show how it works in the code. Okay, let's just have a look at how it is implemented, in fact, in Palabos. So I downloaded the latest version of Palabos. So if you go to the source folder, that is Sportsman folder, there are two new comprehensive model templates. So here you will be able to find all the functions related to collision in the row moment space, the Hermite moment space, central moment space, central Hermite moment space, cumulant, also the Gauss-Hermite formalism that is usually used for the regularized approach and the recursive regularized approach. All collision models are based on 4 functions. The first one always computes the kind of moment that we are interested in. It computes its equilibrium counterpart. It computes the equilibrium function, and it computes the post-collision populations. So if we have a look at the code itself, so at the beginning, what we do is that we define the indices for all the moments. Then we start computing the row moments, for example, if we want to apply the collision in this moment space. So it's like pretty straightforward. So the 0th order row moment is simply the sum of the Fi. First order, it's the sum of Cix times Fi, or Ciy times Fi, etc., etc. Then you compute the row moment equilibrium using standard formulas that are based on the velocity and the density. Here, I renormalized everything by the density. That's why you cannot see. But it appears later in the definition, for example, of the equilibrium, where I multiply by rho. So if we look at the collide function now, so here you have the 4 different, let's say, relaxation frequency. So what we do at the beginning is that we collide all the row moments. Here I'm using 2 kinds of, I'm using 2 parameters for second order moment, because in fact, if you play with the formulas, you can easily show that for particular values of omega-1, you are also able, in fact, to impose a particular bulk viscosity. So here I apply the collision on the second order row moments, third order 1, fourth order, and then I simply use the formula that was described in the presentation. And then that's it. The collision model in the row moment space has been done. If you go to a more complicated one, say let's look at how it works for the cumulant. So for the cumulant, what you do at the beginning is that you do the collision in the cumulant space. Then you come back using standard formulas to the central moment space. Then you come back to the row moment space by converting central moment post-collision moment to the row moment 1. And then you apply exactly the same formula for the post-collision. In fact, it's super simple. And if you want to add any kind of, I don't know, turbulent viscosity or entropy functional, whatever, it would work as simply as that. Let's come back maybe to a presentation. Okay. Okay, so let's continue with some validation. Here, I will show you a comparison at low viscosity that
Sorry, can I ask you a quick question?
Yep.
Did you test the numerical efficiency of all these formulas? Just my interest if it costs much more than, say, a BGK or...
No, not yet. Not yet, in fact, because here what I wanted to do is to make, let's say, the implementation as simple as possible. Because, for example, can you see this? Can you see the code?
No.
Nope. Okay, so I'm not sharing. No, that was my question because I was not sure about what I was sharing. Okay, typically for the formulation of the equilibrium, I mean, in terms of memory, for sure, it's not optimized. Why? Because I'm creating, for example, for the, let's say, the cumulant, I'm creating variables for the cumulants, for the central moments, for the row moments. But in fact, I could, let's say, compile all the formulas, have something that is pretty ugly, but that would be super efficient. And in fact, it's the same for the computation of the equilibrium. I could just impose the formula that I know in advance. So for sure, it's not the most efficient way to code it, but still it's more efficient than if you had to go through all the matrices.
Oh, for sure. It was just to have an idea if how much more it costs, if it costs more. I have no idea.
In fact, it costs more. I don't want to say anything silly, but I would say at most, maybe it's at most 2 or 3 times, I would say. But for the Q9, then you need to, for the Q19 and Q27 in 3D, it would be much more, I would say that it would be much more CPU time consuming. But once again, you can always improve the efficiency because, for example, if you choose, to have omega-3 equals omega-4 equals 1, then there are many terms that just cancel out. So you could, in fact, improve the efficiency, and I will. And why am I talking about this? It's because in particular cases, you do want to impose omega-3 equals omega-4 equals 1 because it drastically increases the stability without, let's say, decreasing the accuracy.
Okay. I mean, it was just to have an idea how much
for
more
sure.
it costs.
No,
okay.
No problem. Yeah, but the main issue is that I'm running most of my simulations on my desktop. So in 2D, I mean, you don't really need to go to a supercomputer to run your simulation.
Totally.
So small validation. So here I'm looking at the convection of an isothermal vortex. Why am I doing this? Because this test case is particularly interesting because it allows you to see if your code is able to propagate information along large distances, in fact. Because what we will do is that we will do 50 rounds of boxes, and at the end of the day, we will look at the shape of the at both the stability of the code and at the shape of the vortices after 50 rounds of boxes. So what I do first is that I use a green mesh composed of 256 points in each direction. I run it for many values of the kinematic viscosity, going from 0.1 to 10 to the minus 6, which is really, really, really low. And I'm looking at the maximal Mach number that is obtained by looking at, in fact, the kinematic energy. So what I say is that the stability criterion is that the kinetic energy should not be higher after, I mean at time t, as compared to the kinetic energy at the initialization. Because in fact, this test case is just pure dissipation of the vortex. So here I'm showing the results in the SRT configuration, meaning that I only have one relaxation time. And what's interesting here is that almost all collision models lead to the behavior of the PGK collision model. but the recursive regularized approach. And in fact, what's quite interesting here is that we are still using this, I didn't talk about this, but in fact, when you use the moment space approach, you automatically use an extended equilibrium that increases the stability of your code without decreasing the accuracy. So this is still quite interesting because here you can see that even if the viscosity is at 10 to the minus 6, we are still able to run simulations up to, I would say, a Mach number of 0.12 or 13, which is not bad, in fact, because the viscosity is super low. Now I consider a second, let's say, configuration for the relaxation frequencies, or this time I will cancel out the high order contribution. And here you can see that we have very different behaviors. We have the central harmonic moments, the cumulant, and the central moment that are behaving in quite a good way, in fact. The recursive approach, well, in fact, when you can cancel out high order moments, you cancel out the recursive computation. So at the end of the day, it's completely useless to use that kind of configuration for this particular approach. But that's pretty interesting, but because that means that here we are able, with two simple configuration, we are able to have 3 different types of collision models that leads to very stable simulations for very low viscosity and very high Mach number. Of course, it's good to have stable simulations, but we also need to be sure that what we are doing is accurate, meaning that there is absolutely no points in propagating information that will have complete nonsense after 50 rounds of boxes, 50 rounds of boxes. So here what I propose is to look at the results for relatively small viscosity, 10 to the minus 4, and a relatively high Mach number. So here are the initial state for 2 different meshes, so using 256 points in each direction and 512 points in each direction. The second column corresponds to the results of the recursive regularized approach, and the third one is the cumulant approach with omega-3 equal omega-4 equal 1. Here I'm not showing the results of the regularized central harmonic moment approach because, as I said before, it is exactly equivalent to the SRT-RR approach. So what you can see here is that after 50 rounds of box, in fact, results are quite impressive, even with the 256 point per direction computation, because we have some numerical anticipation, we have a bit of dispersion because the vortex are not round anymore. But still, that's quite impressive regarding the value of the viscosity and the Mach number. And in fact, you can clearly show that these are purely numerical effects, because if you use a finer mesh, in fact, this discrepancy are getting are reduced. Sorry. So in fact, this is pretty interesting because we can show here that there are collision models that are able to run simulations for very low values of the viscosity and relatively high values of the Mach number. Of course, there is, in fact, no point in doing simulations with values of the Mach number that high in practice. Why? Because you would also need to take into account the temperature fluctuations. But what it's interesting here is that, in fact, you can show that if locally you have an acceleration of your flow, for example, let's assume that you are running a simulation around the landing gear during landing phase or takeoff phase, the Mach number is close to 0.2, 0.3, but locally it will increase up to 0.5. And if your scheme is not stable at 0.5, in fact, your simulation will crash, even though in most of the simulation domain, the Mach number is close to 0.2 or 0.3. So this is particularly interesting, in fact. So what I talked about here, in fact, this formulation in 2D, they have already been merged to the Palabos GitLab repository. Right now, I'm working on this formulation. So here I'm talking about what is already available. So you have the D2Q9 formulations, and you also have access to previous collision models that are available in Palabos in 2D and 3D. So you have MRT formulation, you have the recursive-regularized, the entropic formulation, you also have a KBC, and you have also access to some subgrid scale models. What still needs to be done, or what is in development, are the implementation and the validation of the 3D formalism of what I've just presented. I'm also working on the extension to dynamic formulation, just to include entropic, KBC, subgrid scale model, or whatever, to this unified formalism. And we are also working on a, let's say, a solver that is based on GPU in order to further accelerate the simulations. And this is the end of my presentation, and I thank you for your attention. Do you have any question?